So we had a series last time. I simulated it. N was 128, and what theta 1 and theta 2 values did you give me? 0.3, 0.7? I asked you to give me a number. 0.7, 0.4. 0.7, 0.4. Okay. Because I did that on the terminal and I forgot to save the values, but I have it here. Start our studio. Hopefully it's there in history. If not, all good. So what we tried to do, well, how did we get those two equations?
We took the equations for row 1 and row 2, substituted in the values that we had.
We had row 1, we had row 2, plugged it in row 1, row 2, did we subtract, did we add? Row 2 minus row 1, row 1 minus row 2? Or did we just use the equation? I think we subtracted, correct?
We subtracted and we divided.
Yeah. Okay. Subtract, divide, and same thing you could do with addition. You could add row 1 plus row 2, try to come up with a system. Regardless, in this case, we have theta 1 minus theta 1 theta 2. I see the same term over here. I'm going to take this, put it in there. So minus 4. Minus 0.164. If I pull that out, I would have theta 1 minus theta 1 theta 2 plus 0.569 theta 2 equals 0. Well, that is simply 3.469. Take that, put it in there. When you multiply those two, it would come to 0.469. With a negative. Move points, negative 0.569 theta 2 to the other side. It is going to become positive. And eventually we would have 0.569 theta 2 equals 0.569 theta 2. Get rid of 0.569. Theta 2 equals theta 2. What a great conclusion. What a great way to estimate stuff. Right? Is that useful? No. So what we have is a nonlinear system. Nonlinear systems typically require 99.99% of the time, unless you design it in a specific way, intentionally, you have to use an iterative procedure. Comtech. Did you do Newton-Raphson? We did. That was your final. Newton-Raphson was your final, but I didn't say that it was Newton-Raphson. That we do optimization. Basic optimization. If you have a parabola and you want to find an optimum value, how would you do it?
Derivative equal to 0.
You go ahead, Andres, didn't mean to interrupt.
No, just.
That's it. Derivative equal to 0, find the critical value, test where it's increasing, decreasing. So pretty much the derivative plays a role, but we're not going to take that approach to solve this nonlinear system. Computationally, you can update and minimize something. Even the derivative approach, if you are into artificial intelligence, machine learning algorithms, one of the most important ones is gradient descent. Gradient is nothing but derivatives in higher, shouldn't say higher order, higher dimensions. We can do that, but I'm going to make a linear convergent procedure. Linearly convergent, quadratically convergent, exponentially convergent, which is going to be faster in terms of convergence. We know what convergence means, right? Converge to some value when you have a series, sequence. Which one would converge faster? Linear, exponential, quadratic, exponential. And exponential is the most difficult. Linear is the easiest, but slow. It's very slow computationally speaking with higher order models. So AR models use recursion, and MA models use iteration or iterations. They are different in the sense iteration or iterative computation. No, I want to keep it this way so we can relate with recursion. Iterative computation requires step-by-step updates of values with respect to some other coefficient, cost function, variable, whatever that might be. So we had issues here because we didn't know one quantity. And I said, had we known that one quantity, we would have had the answer easy. What is that? One quantity. Sigma squared A. Noise variance. No one's got a clue about that. I can make an assumption, but will it result in a good fit? Probably not. So, our goal has to be finding sigma squared A. Again, mind you, you could do ρ2 minus ρ1, ρ1 minus ρ2, ρ1 divided by ρ2, ρ1 plus ρ2, end up with a system. You can try to solve it, manually. Won't work unless you have some conditions. So start with an initial step and pick values for θ1 and θ2, because that's what we are trying to estimate. What is the easiest value that you can think of for θ1 and θ2? 1. 0. That doesn't make sense. Oh, it will too. We are going to pick 0. But 1 is okay also, but I'm going to pick 0. Later, I would explain a condition which would help a lot. So θ1 would equal θ2 equals 0. And if we did that, we know sigma squared A times 1 plus θ1 squared plus θ2 squared equals gamma naught. The same thing happens with calculus 1 when I ask students, pick an easy number that is less than 2 so that we can test for critical values. they give me 1. Now, why not 0? Rewrite will have sigma squared A equals that. We know that this formula holds true for any order. If theta 1 is 0, theta 2 is 0, denominator would become 1. So gamma naught over 1, which would simply be gamma naught. We know the value for that, which is 1.53. Next step, or step within this step, is to use rho 1 or gamma 1. It is a matter of choice. So what I'm going to do is write it in terms of gamma 1. All that happens is we're not going to divide by 1 plus theta 1 squared plus theta 2 squared. If you look at our derivation, gamma 1 was simply sigma squared A times negative theta 1 plus theta 1 theta 2. Right? We got all that 1 plus theta 1 squared, theta 2 squared business because we divided by gamma naught. We tried to use rho directly because rho 2 minus rho 1, rho 1 plus rho 2 could help. Not always. So now that I know 1.54, I can divide gamma 1 by sigma squared A that would give me negative theta 1 plus theta 1 theta 2 equals gamma 1 over sigma squared A. Good. One more item, gamma 2 would equal negative theta 2 sigma squared A based on our derivation. Divide by sigma squared A. Move the negative, we'll have negative gamma 2 over sigma squared A. And you might say, well, theta 1, theta 2 is 0. Let me just plug in 0 here, 0 there, and get to an answer. You are going nowhere. Do you agree? So the idea is to start at the last coefficient. So here it is theta 2. If it is MAQ, you would start at theta Q and go backwards. So we're going to start here. Negative gamma 2, negative 0.253 over 1.54. We'll do it again. Negative 0.563. 1.64. Good. Now we take that value, plug it in that equation, solve for theta 1. Which is gamma 1, 0.876. over sigma squared A, which is 1.54. Theta 2 is negative 0.164. What is that number? 0.6 something.
0.569.
569. Okay.
With 2.876 divided by 1.54.
0.876 over 1.5.
Yeah. 569.
Combine those two, you have negative 1.164. Theta 1 equals 0.569. Theta 1 would be minus 0.569 over 1.164. Good. Negative 0.54. Calculate.
Oh, sorry. 2.489.
Keep overestimating it. Erase.
I noticed from phase 2 value that we solved for is equal to rho 2 times negative 4. Is that a normal occurrence?
Times negative 1.
Yeah, it's literally just negative rho 2.
That's where you initially start. Now, the question that we need to ask is, when I simulated the series, theta 1 is 0.7, theta 2 is 0.4. The very first step, I end up getting negative numbers. Yes? So you might wonder, well, how do I go from here to there? Well, you don't have to. This is simulated using R. In R, the way the model is defined is you have the autoregressive part with minuses, the moving average part with plus. Remember, I said depending on the textbook, some would use minus, some would use plus. We stuck to minuses for the autoregressive side, minuses for moving average side. Some of you are giving me a look. This is what I'm referring to. Right? And that is theta 1, that is theta 2. 3, 1, 3, 2. Right? In R, 3 1s are okay, they have negatives, but the definition for the MA side is actually plus. Doesn't change the theoretical idea behind it. We can simply write it as 80 minus 6. 80 minus 1 minus 4, 80 minus 2. Right? So all of our formulas, the derivations that we did, is based on a model of that sort. So naturally, I should be expecting negative numbers. Does that make sense? So again, depending on the software, the definition of the model could be minus on this side, minuses on that side, minus here, plus this there. I personally think it is easier if you just kept it as minuses on this side, minuses on that side. This way, the characteristic polynomial sort of has the structure. Do we understand what's happening? Do we understand why we are getting negative numbers? Okay. There is. At the very end, we can multiply by negative 1. Step 2. You should always start with sigma squared A, because that is the value which causes problems. So sigma squared A would equal to 1.54, which is gamma naught, over. What do you think that we should put for theta 1 and theta 2? The values from the initial step. So negative 0.48 squared plus negative 0.164 squared. We need a calculator. Or I could do it at home. You're all being very helpful. $1.222. Good. Theta 2 would equal to negative gamma 2 over sigma squared A. Keep in mind, you've got to follow this process in order or in the specified order. That's what's creating the problem when we try to solve it. So we take care of that first. And you've got to go backwards, otherwise you would simply end up with theta 1 equals 0, theta 2 equals 0, and you're stuck at the initial step. You're not going to move ahead. So theta 2 negative 0.253 over 1.22. And what is that? Negative 0.22.
207.
207.
Yeah.
21. Onward, we have negative theta 1, theta 1, theta 2 equals gamma 1 over sigma squared A. Let's go ahead and simplify this. Theta 1 times 1 minus theta 2 equals gamma 1 over sigma squared A. It should be a negative one. I'll do this instead. Oh, that's positive. Well, there is some negative there, but I'm just rewriting it so that we can make computations easier. Theta 1 would now equal to gamma 1, which is 0.876 divided by sigma squared A. Which value should you use?
1.22.
1.22 times theta 2 minus 1, so minus 0.21 minus 1. What's
0.59.
negative 0.59? The second step. Onward to the third step. Where should we start?
Sigma squared
Sigma squared A. The numerator, the autocovariances do not change. So 1.54 over 1 plus theta 1 squared negative 0.59 squared plus negative 0.164 squared. You can just give me what that's probably is.
Hold on, is it, are you theta to negative 0.1?
Oh, sorry, I don't know. Looking at red, okay, negative 0.21.
1.11.
Okay, 1.11. What is the next item to compute? Theta 2. Negative 0.253 divided by 1.11 this time. And what do we get? Point 0.23. Second.
Negative 0.23.
What's the next decimal? 7.
It's 227.
227. Can I erase this one? Yes. Theta 1 would equal to gamma 1, which is 0.876, divided by sigma squared A, mind you, it has to be the new value, 1.11 times theta 2, negative 0.23 minus 1. Which is
Negative 0.64.
come again?
Negative 0.64.
Negative 0.64. On to step 4, what should we compute first? Sigma squared A. So 1.54, the numerator, that doesn't change, over 1 plus theta 2 from the previous step, theta 1 from the previous step, squared, what do we get? 0.095.
It was 1.05.
0.5. 0.59, so like 0.06. Find theta 2, which is simply negative gamma 2, so negative 0.253, over the new sigma squared A, 1.06, which is approximately negative 0.24.
Negative 0.24, yeah, 238, yeah.
theta 1, that's that, gamma 1, 0.876 divided by sigma squared A 1.06 times theta 2 negative 0.24 negative 1. What do we get?
Negative 0.67.
Step 5, repeat the process again. 1.54 divided by 1, the new value of theta 1, negative 0.67 squared, plus negative 0.24 squared. What do we get?
One point, 022.
1.022. Theta 2 is gamma 2 over sigma squared A. So gamma 2 would already have value 0.253 divided by 1.022. What do we get? I forgot the negative.
Negative 0.25.
One more decimal, Joe.
Well, then it's negative 0.248.
Trying to increase position for a reason. Saying gamma 1 over sigma squared A, theta 2 minus 1. Increasing position and decreasing the size of the letters that I'm writing for a reason. Gamma 1 is 0.876 over 1.022 times minus 0.248 minus 1. What do we get?
Six, 8, 7.
Okay. Step number 6. Sigma squared A would equal to 1.54 divided by 1 plus negative 0.687 squared plus negative 0.248 squared. What do we get? Okay. 1.004, and I'm just going to call it 1.00. Good. Now, if we do this using R, we're going to increase the position, wait a bit longer. You know, we don't have that much time. So theta 2 would be negative gamma 2 over 1.00. Well, I take that back. 1.004, because I want you to see something. 1.004 What do we get?
Negative 0.252.
256. Was that negative 0.248? Strange. Perhaps because of granting, but I am going to stop it. 0.876 over sigma squared A in this step is 1.004 times theta 2 minus 1 minus 0.252 minus 1. It's a good thing I've reduced the size of my x's. What do we get?
697.
Negative 0.697. So again, going back to, did someone ever try a machine learning algorithm of some sort? Or any iterative procedure? Error? Okay, what is needed in an iterative procedure?
Tolerance.
You need tolerance and or either
Like a number of iterations to stop.
number of iterations that you need to stop. So there are two ways to do or identify a stopping condition. One, tolerance. Two, number of steps. Tolerance simply means there are many ways to define it. The difference in the estimate between the current value and the previous value. How small do you want it to be? How much can you tolerate? Hence tolerance. Same theta 1 at this step versus theta 1 in the previous step. You can either do theta 1 minus theta 2 squared to determine tolerance, you know, L2 norm, L1 norm. You could use one of those. And if you reach a certain tolerance, you stop. I am satisfied with the tolerance. I'm tolerating what I'm seeing. And if this doesn't work out and we keep on going back and forth, looking for optimal coefficients, and in that case, the algorithm keep on running, and we don't want that. So we put a maximum number of steps. If you did neural networks machine learning, typically 1,000 steps, and you stop. The bigger the network, the fewer the steps for computational sake. Now, something is happening here which makes theta 2 and theta 1 get closer and closer and closer. What is happening? What was trouble at the beginning? What we knew as trouble when it came in? Sleep did his
The sigma squared.
sigma squared A. 1.22, 1.11, 1.06, 1.022, 1.004. What do you expect to get eventually? 1. If you get 1, no matter how many steps you go past it, you get the same theta 2, right? If you get the same theta 2, you are going to get the same theta 1, correct? It has to stop because you will end up getting the same value over and over. So that is a stopping condition when sigma squared A approaches 1. You would end up converging. You may ask, well, if the condition is that sigma squared A equals 1, why didn't we just start with sigma squared A? It's a natural question to answer, right? Right, okay. I erase step one. But we have step two. If sigma squared A is 1, you would have the autocovariance value to be theta 2. And theta 1 would be dependent on that value, that would be 1, and whatever number you have would still depend on the autocovariance. Yes? Now, what do we know about autocovariance? Depending on the series, it could go all the way up to negative infinity to positive infinity. Correlation is between -1 and 1. Covariance, autocovariance, is from negative infinity to infinity. So pretty much you end up with a wrong estimate. It is feasible. How do we know? Well, we did time series to make a forecast, correct? Well, if you are going to fit a model and get a forecast, whatever you fit must be or should be a good model, correct? If you start with an awful model, whatever forecast you make is going to be awful. Yes? Hurricanes, spaghetti law, right? Some models are great, some are just awful. Statistically speaking, 2 of them always came close. Do we know which 2?
European model.
The European model and the United States model. Those are the only 2 statistically that are consistent. Of the 2, one is more consistent. The European model, always. I wouldn't say always, 99% of the time, European model is more consistent than the US model. So, if you're making a forecast, you've got to have a good model. So if you assume, oh, the noise is 1, but in reality, the noise is a different value, you are providing wrong estimates. Wrong estimates would imply a poor fit. A poor fit would imply a poor forecast. Useless. Does that make sense? Okay. So we got lucky here. If you don't change your mind, go to graduate school in math stance, you can look at convergence chords, and in this case, the convergence would happen in a linear manner. The other approaches, for example, quadratic convergence would go like this. Exponential would drop really fast. So instead of going, 6 steps, perhaps you would be done in 3 steps or 2 steps. Convergence can be achieved right away. But of course, there is no such thing as an easy launch or free launch. As you try to improve computational speed, the trade-off is the algorithm is more complex. I'm not going to do quadratic, it will take forever. Are we clear? Yes? So our final estimates for θ1 and θ2 are negative 0.697 and negative 0.252. If you say, well, I'll just round it to 1 decimal place, which you should never do, but if you did, are we satisfied with the estimation that just happened?
Should we be concerned about that both of our estimates are negative and both, so once we input it are positive?
Yes, we should. Because in R, if you are doing it in R, you've got to flip the sign at the very last step. Right? You simulated the series in R. We are using all the derivations that we did in class. So our models use negative θ1, negative θ2, our convention notation. Our convention is positive θ1, positive θ2. So If you are doing manual calculations and then trying to fit it back in R, you've got to flip the sign. Does that make sense? So, we can program. So technically, since we simulated it in R, if we have to go back to R, those two signs need to be fit. And if I can, push it and just round it to the 10th place, I'll end up getting 0.3 and 0.7. Isn't that nice? Those are the values that I started. But I'm being too loose with rounding. If you take a course in computational statistics, rounding is an issue. You can't simply round your way out of tricks. You have to maintain precision. So if we did this using a computer, it is not going to convert properly in 6 steps. It will probably take about 12 or 13 steps. Good? Does that make sense? By precision, I mean 9 decimal places at minimum, 9 decimal places at minimum. In which case, eventually it will converge to the actual values, 12, 13, 14 steps. Are we clear? Okay.